Hello, everyone. We are going to be doing Atari 800XL assembly language programming on the 6502 CPU. This is like chapter 4 of this series. So basically, if you haven't followed the others, you can see it in the description. I'll have a link to the series, the first episode, basically where we learned pretty basic stuff like binary numbers and stuff like that. But now we're actually, and we learned about the 6502, their registers, those kind of things. But now we're ready to start learning what assembly language actually is. So that's pretty exciting. My name is Elise, and I do these series on a few different topics. I'd like to do even more, but let's get done with assembly language first. We are using Atari Roots. It's on my browser right now, so you can follow along. You can read it, whether you want to like watch me read it or like you can just like read it on your own and find that if you ever get stuck, you can kind of find the part of the video where I'm doing the same thing. Like that's one way to do this. It's all up to you. And we are emulating the Atari in Altera. That is already set up. We did that in a previous video. Um, and what was the other thing? We're going to be using the Max 65 assembler, and that is also, all of this is in the description. If there's any questions, I also have a Discord server you can join and ask questions there, or you can put it in the comments. So let's just get going. I'm going to read off of the PDF instead of the browser because it looks a little bit more authentic. So here we go. Chapter 4, Writing an Assembly Language Program. Here it is at long last. And yes, it really feels like at long last, Like I felt bad for you all trying to follow with all this because if you already know binary numbers, then it's like, why are we going through this? But anyway, the assembly language program we promised you. A program you can type, assemble, and execute without having to rely on any basic commands. The program was written on an old battle-scarred Atari 800 computer using an Atari assembler editor cartridge almost as ancient. It's funny because this book is ancient and they're talking about ancient, right? But the program will run on any Atari computer, and like all of the programs in this book, it is totally compatible with both the Atari assembler editor cartridge and the newer, faster Max 65 assembler. That's what we'll be using. With a few minor but critical revisions, such as eliminating line numbers and changing the star equals $0600 directive in line 40 to the org $0600. This program and all of the others in this book can also be converted into programs that will work with your Atari macro assembler and text editor. But unless you're already an assembly language programmer, I strongly recommend that you type, assemble, debug, and edit the programs in this book using an assembler, more like the ones they were written on, the Max 65 assembler. So I think there's a very popular basically workflow where you use Eclipse with a plugin and it does everything and then it can like send it over to the emulator and you run it. But part of this for me, this experience, I never had an Atari computer. I'm not familiar with it. My friend had an Atari computer, so I saw some of that, but I have no idea what they are. Um, I just bought an A400 Mini to kind of learn about it a little bit more. Hi, Isabel. I just decided to like, why not stream at the same time so that people actually believe that I do this for real and it's not. Well, anyone who watches my videos can tell for sure that these things are like are done real time because I'm lost so much. Anyway, so you don't have to stick around. Don't feel bad. Um, I am doing this Atari stuff. So let's continue. Here's the program we'll be working with in this chapter. As you can see, it's a very simple program for adding 2 and 2. So this whole thing is to add two numbers together. This is very long for a program that adds two numbers together. Let's take a look. Oh, by the way, if you're still there, Isabel, does this actually like work? You can see the screen just like the video and everything. I've never done a YouTube live before. Anyway, um, let's take a look. Let's take a close look at it and see how it does what it's supposed to do. An 8-bit addition program. Well, 2 is definitely less than 256, and the sum of, 2 and 2, which is 4, is less than 256. So we know we won't have to worry about carries and overflows. We can do everything in one 8-bit register or memory address. So these look like they're comments. This is probably the name of the program. This, I'm guessing, is the address of the memory where it starts. And then some stuff. Load accumulator. What was this one? I keep thinking League of Legends ADC. This is carry, add with carry or something like that, I think. And then store into this memory address. Return subroutine. Clear D. This must be something. Anyway, I'm sure they'll tell us everything. Look closely at this program and you'll see that the numbers it's supposed to add 2 and 2 are in lines 80 and 90. That's true. After the program adds 2 and 2, it stores the results of its calculation in memory address CB, or 203 in decimal notation. Yeah, so the $ means it's a hexadecimal number. That happens in line 100. Some of the instructions in the program may look familiar. Let me make sure may look familiar. We've touched on most of them in the preceding chapters, but there are a few items in the program that are encountered here for the first time. These include the semicolons in the first few lines of the program, the asterisk equal directive in line 40, and the dot end directive in line 120. All right. As you can see more clearly in the explosion diagram that follows, the program source code listing is divided into 4 fields or columns. 4 fields or columns. 1, 2, 3, 4. No. Oh, no. Line number, label, opcode, operand, remark. So it's 1, 2, 3, 4, 5. But maybe 5 doesn't matter. Let me do something here. All right. If each field had a heading and if the program listing weren't all jammed together, here's what you would see, right? Okay, that's great. Only an example. The above listing is provided only as an illustration of what a source code listing would look like if it's 4 fields, line numbers, labels, opcodes, and remarks. Wait, so what did we miss? Line numbers, labels, opcode, and remarks. Oh, operand it didn't list separately. How are we supposed to know that, right? Like that totally looks like a separate thing. Anyway, line numbers, labels, opcodes, and remarks were clearly separated into columns. It's like the sun keeps coming in and out, so I don't know if it changes like the camera a lot. Anyway, actually, no one writes source code listings this way. Well, we'll prove them wrong. When you write a source code listing using a Mac65 or Atari cartridge, the usual way to do it is to type your fields in a format that is rather jammed together, crammed together so tightly, in fact, that the columns don't line up at all. Once you get a little practice writing code in this format, though, it practically becomes second nature. Well, that's good news. Maybe I'll get a lot better at like accepting bad-looking programming languages after this. We'll see. These are the rules. Line numbers. When you write a source code listing using Mac65, I'll just say Mac65 because these guys like repeat things a lot, but it means Mac65 or Atari Assembler Editor cartridge. Each statement or line must be assigned a line number. So this is just like basic, right? I don't know basic, but I know like 10. Oh, yeah, I know enough to do 10 print hello world 20 go to 10 run. That much I know. And I know that they need line numbers. Line numbers aren't really necessary in assembly language programs and are not required by some assemblers. The Atari macro assembler and text editor package, for example, doesn't require the use of line numbers and won't assemble a program that includes them. Yeah, that's interesting. So, like, I don't know why Atari has a macro assembler and text editor package and also an Atari assembler editor cartridge. Like, why do they have two products that do the same thing? No idea, but it doesn't matter. We're using the Mac 65. When I looked on the forums, it sounds like that's the best one, other than the Eclipse plugin, but we want the authentic experience. The line numbers in front of the first column of our addition program progress in increments of 10, just like the numbers in a typical basic program. Yep. They don't have to be written that way, but as is also the case in basic programs, they usually are, line numbers can range from 0 through 65,535. And we learned in the long binary chapter that this is the largest 16-bit number unsigned number you can have. So that makes sense. How are you guys doing? No one's talking. I feel lonely. All right, labels. Labels, if they are used, occupy the second field in assembly language statements. Exactly one space, not two. We're basically almost like... Uh-oh, I have other sounds on. I forget. Anyway, so I don't remember what I was saying. Exactly one space, not two, must be left between a line number and any label that follows it. If you start a label 2 or more spaces after a line number, or if you use your tab key to get to your label field, you may clobber your program. Wow, like, I don't know if you guys have been following my Nix series, but I don't know how many videos I have. I might have like 10, 15, maybe 20 videos on Nix. I literally cannot remember to put the semicolon at the end of each line. So I feel like this is going to be really painful for me. We'll see how well I can remember. In assembly language programs, labels are used to identify the first lines of routines and subroutines. Our program for adding 2 and 2, for example, is labeled ADD NRS in line 60. Let me bring that up. I had the foresight to basically type in the program. I'm so proud of myself. So that we can reference it later. And we can see in line number, where is my terminal? Line number 60 here. Wait, didn't it say in line 60? Oh, this is line 70. You know, oh, it said 60 here. Somehow I did this wrong, I guess. 40 has this, 50 has this, 60 has CLD. Oh my god. So I had the foresight, but wait a minute. Where did this come from? No, look at this. 60 CLD. That's what was here. So 60 is CLD here, and then when they blow it out, it's no longer CLD. Guys, like, seriously, right? Like that is not good. But anyway, the point is that we see here, I think the CLD was supposed to be here, maybe. CLD, yeah. So here we can see that this is clearly one column more to the left than the others. And so ADD NRS is definitely the label. Okay, so we figured that part out. Well, we haven't figured out why they screwed up. They couldn't copy something correctly, but we figured out that I'm not totally insane. I have some sort of like semblance of self respect still. Since our program has a label, the program could be used as a subroutine in a longer program. Oh, this makes me really want to do this for Advent of Code now. And could easily be accessed by its label. Several kinds of assembly language instructions could be used to call it. For example, JSR ADD NRS, jump to subroutine at label. BCS, I don't know BCS, branch on carry set to label. That's very easy to remember. GMP ADD NRS, jump to label. In the first example, ADD NRS, what, can someone help me? What does the NRS stand for? Like, just so that I don't have to say it. Add numbers. Add numbers. Oh my God. NRS for numbers. Is this thing still working? Yeah, I think so. Well, we'll see. If it screws up, it's okay the first time. In this first example, add numbers would end with the RTS return to subroutine instruction in line 110. Oh, that's right. Here we have return to subroutine. Return to subroutine performs the same kind of job in assembly language that the return instruction performs in BASIC. Well, I hope they don't keep making BASIC analogies. I don't know BASIC. It signals the end of a subroutine and returns control back to the main body of the program. In the latter examples, a second branch or jump instruction would be used to transfer control instead of RTS. I don't know what latter example means, but we'll continue. We'll discuss jumping, branching instructions, and subroutines at greater length in later chapters. For now, what's more important to remember is that when you type a source code listing on a Max65 assembler, one space and only one space must be used to separate each label. You use it from its line number. A label can be as short as one character and as long as the length of a statement permits, 106 characters minus the number of characters in the statement's line number. Okay. Most programmers use labels 3 to 6 characters long, hence the add NRS. Operation code mnemonics. An operation code or opcode mnemonic is just a fancy name for an assembly language instruction. There are 56 opcode mnemonics. That's really not too bad. Like, it's not too many. I can imagine memorizing 56 things. And they are the only ones that can be used in Atari assembly language instructions. Opcode mnemonics such as CLC, CLD, LDA, ADC, STA, and RTS are typed in the opcode field of assembly language source code listings. When you write a program using a Max65 assembler, each opcode mnemonic you use must start at least 2 spaces after a line number or 1 space after a label. Yep. They've said this many times. I think I can start to remember this. An opcode mnemonic placed in the wrong field will not be flagged as an error when you type your program, but will be flagged as an error when your program is assembled. All right, so it doesn't know that it's an error. It's not like in editor, it's not like you're using an IDE and it's like, oh, this is wrong, but when you try to actually compile or assemble, it'll tell you. The opcode field in a source code listing is also used for directives and pseudo ops, words and symbols that are entered into a program like mnemonics but are not actually members of the 6502 instruction set. Directives and pseudo ops. Oh, I didn't know about these. The asterisk in line 40, right here, of our program is a directive, and the .end statement in line 20 here is a pseudo-op. All right. The asterisk directive is used to tell your computer where an assembly language program is stored in memory after it is assembled. The .end directive is used to tell the assembler where to stop assembling and to end the assembly language program. Okay, cool. So most likely every program's going to need one of these stars and ends. It's kind of like a begin and end, right? Let me check one thing here. All right, cool. Operands. The operand field in a Max65 assembler program starts at least one space or tab after an opcode mnemonic. Operands are used to expand opcode mnemonics into complete instructions. Some mnemonics, such as CLC, CLD, and RTS, do not require operands. Others, such as load accumulator, store accumulator, and add with carry, maybe, do require operands. We'll be providing much more information about operands later. So these must be operands here. Like, we have two spaces after the line number, we have the opcode, and here's the operand. Same thing with this one here, line 90 and 100. All right, comments. Comments in assembly language programs are like remarks in basic programs. They don't affect a program in any way, but are used to explain programming procedures and to provide saving space in program listings. There are two ways to write comments in source code listings written on the Max65. One method is to put comments in the label field of a listing preceded by semicolons. So that's what we see here, right? This is the label field because it's one space after the line number. Right. We read this. The other method is to put them in special comments field that occupies what's left of each line following the instruction fields, the opcode, and the operands. So if you use the comments field at the end of a line and don't have room there for the comments you want to write, you can continue your remark on the next line simply by typing a space, a semicolon, and the rest of your comments. All right. Examining the program. Now that we've looked at our sample program field by field, let's examine it line by line. Let us do that. Lines 10 through 20, 10 through 30 are comments. Yeah, so we have we get that. It's a semicolon where the label field usually would start. The directive, line 40. The origin, this is the origin line of our sample program. They don't tell us what origin means, but I guess, we'll learn more later. Every assembly language program must start with an origin line. As you may remember from chapter 1, the first thing a computer does when it runs a machine language program is to go to a predetermined memory location and see what it finds there. So when you write an assembly language program, the first thing you have to do is tell your computer where to start looking for the program in its memory. When your assembler encounters an origin directive, it will set the program counter of your computer's 6502 processor to the address given in the directive. I see. So remember in the last video with this inside the 6502, there was a program counter, which I think was a 16-bit address because it's memory, and that's what this line will modify somehow. Right, the first instruction of the program will then be loaded into that memory location, and the rest of the program will follow in sequence. The origin directive looks like a simple line to write, but deciding what number to put in this line can be a very tricky job, especially for the beginning assembly language programmer. There are many blocks of memory in your computer that you can't use for assembly language programs because they're reserved for other uses. For example, to hold your computer's operating system, disk operating system, basic interpreter, and so on. This is so funny because we've moved on to Rust and all these safer languages. There was VMs and then Java and stuff, and now we have fast memory safe programming languages. And here it's no, we're just we can go in and touch the ROM, we can go in and touch operating system and stuff like that. That's insane. But yeah, these are like, it's a different time. Even the assembler that you'll use to write this program takes up a block of memory space that's forbidden territory for you. At least until you become familiar with certain landmarks you can use to find your way through the jungle of your computer's memory. That's funny. I never really thought of it as so complicated. Even in C, the old days, you just call like malloc or something like that, and you get like a chunk of memory. You don't have to know too much about where it's getting it from. Until then, there does happen to be one small block of memory that's reserved under ordinary circumstances for just the kind of short user-written assembly language programs that we're going to be working with in the next few chapters. The block of memory is called page 6 because it runs from the memory address 0 hex 0600 to 06FF. Okay, so it's like basically as far as you can go with the 06 in front. It's from 00 to FF, so that makes sense. Page 6 is only 256 bytes long, but that's more than enough space for the program we're going to be working with in this chapter. Can you imagine 256 bytes being enough? Damn, that's crazy. Sorry, it just blows my mind. All right. For the program we're going to and for the other programs that we're going to be working on for the next few chapters. Wow. Later on, as your programs grow longer, you'll learn how to move onto larger blocks of memory. Line 40 in our sample edition program tells your computer that the program you're going to write with will start at memory address 0600. So there we go. That's line 40. Line 50, blank line. This comment line just separates the origin line from the other lines in the program. The white space looks nice, doesn't it? I think they mean like, just like having a little separation. I don't know that I agree. It just feels like maybe that's an assembly language programmer thing. Line 60, ADD NRS CLD, clear decimal mode. Right, I remember that now. ADD NRS, we've just used a label field in this line to name our program add numbers. So if we ever decided to use our program as a routine or subroutine in a larger program, it will have a name. Then we can address it by its name if we wish, instead of by giving by its memory location. It is usually good programming practice to give labels to important routines and subroutines. A label not only makes a routine easier to locate and use, it also serves as a reminder of what the routine does, or until your program is debugged, what it's supposed to do. Oh, that's cute. CLD. We're using plain binary numbers in this program, not binary coded decimal numbers. So in this line, we'll clear the decimal mode flag of the 6502 process status register. The decimal flag need not be cleared before every arithmetic operation in a program, but it's a good idea to clear it before the first addition or subtraction operation in a program, since it may have been set during a previous program. We learned about this in the last video inside the 6502, that there is a status register with lots of bit flags, and this is one of them. And I think it said basically we're almost always going to want to do this. In the original one, code, like it did this in line 60. I guess like I can see why, because you only need to do it once during the whole program. If you did it every time in the subroutine, then it would like always have to switch it off, and probably it's not needed. Yeah. So anyway, I think either way will work. If you had another subroutine somewhere else that actually set it to binary coded decimal, then you'd be screwed. So maybe it is better to put it in the same line as the label, even though it's an extra like operation you're going to have to do each time. All right. Did we do this already? Yeah, we already talked about this. Line 70 CLC. Uh, the status register's clear carry flag is affected by so many kinds of operation that it's considered good programming practice to clear this flag before every addition operation. It takes only 1/2 of a millionth of a second and just 1 byte of RAM. Compared to the time and energy that debugging can cost, that's a bargain. Sure is. So that's pretty clear. It sets a carry flag whenever you do addition, or it could. So if your previous one set that flag, you should clear it here before you're doing anything. Before you do any arithmetic operations. All right, line 80, LDA number 2. That is still line 80 for us. Load accumulator with number 2. And I think this means decimal number 2. This is a very straightforward instruction. The first step in an addition operation is always to load the accumulator with one of the numbers that is to be added. The hash sign in front of the number 2 means it's a literal number, not an address. If the instruction were LDA2, then the accumulator would be loaded with the contents of memory address 0002, not the number 2. Alright, so that makes sense. This means literal, and by default, I think it's decimal. Unless you put a dollar sign in front of it, then it's a hexadecimal thing. Okay, continuing on. Line 9080C number 2, hash 2. Add with carry the number 2 to the accumulator. Okay, add with carry the number 2 to the accumulator. This is also a straightforward instruction. ADC number 2 means that the literal number 2 is to be added to the number that's in the accumulator, in this case, another 2. As we've mentioned, there is no 6502 assembly language instruction that means add without carry. So the only way that an addition operation can be performed without a carry is to clear the status register's carry flag and then perform an add with carry operation. All right, so when we add numbers, it's always add with carry. They could have just called it add and just said like, hey, adds are always with carry. How is everyone? Drinking some coffee today. I usually have coffee in the morning, and then like later in the day I switch to tea because I don't want too much caffeine. Also, just tea tastes better in the afternoon. I know most people are like, I'm a tea person, I'm a coffee person, and you're like hardcore, but I like both. I think that's a theme in my life. Like, I don't like one thing. Like, even this, like retro stuff and like totally new stuff, I love both. I love it. I love everything. I don't even have like favorite language or anything. Vanilla or chocolate though, I like vanilla. Okay, so now we're on line 100. Store accumulator in memory address CB. Store $CB. Got it. This line completes our addition operation. It stores the contents of the accumulator in memory address $CB, which is decimal 203. Note that the symbol hash is not used before the operand CB in this instruction, since the operand in this case is a memory address, not a literal number. Right? You're not storing a number. You're storing the accumulator into a memory address, so you don't use the hash. Oh, we're almost done. Line 110 RTS, return from subroutine. If the mnemonic RTS is used at the end of a subroutine, it works like a return instruction in BASIC. It ends the subroutine and returns to the main body of a program, beginning at the line following the line in which the RTS instruction appears. But if the RTS is used at the end of a main body of a program, as it is here, it has a different function. Then, instead of passing control of the program to a different line, it terminates the whole program and returns control of the computer to the input device that was in control before the program began, usually a cartridge, an operating system, a keyboard, screen editor, or a machine language monitor. All right, so isn't that sort of like, do we need an end then? Well, maybe the end is for the assembler, not for it's not for the machine language code. Line 120 dot end directive. Just as the asterisk equal directive begins an assembly language program, the dot end directive ends it. It would be nice if it was a little more symmetrical, like they look so different, right? The begin and end should kind of look more similar to each other. The .end directive tells the assembler to stop assembling, and that's exactly what the assembler does. Even if there's more source code after the .end directive, the .end directive can therefore be used as a powerful debugging tool. You can put it wherever you want in a program you're debugging, and that's where the assembler will always stop assembling until you remove the .end directive. When you finish debugging your program, you can use the .end directive to bring the routine neatly to an end. Before you can do that, of course, you must remove any leftover .end directives that may still be hanging around. That is, if you want your final program completely assembled. That's kind of dangerous. It's kind of funny, like, the assembler ideally would tell you if you have, like, hey, here, I noticed that you still have, like, multiple .ends, but I guess it doesn't tell you that. So, gotta be careful. When debugging is complete and your program is finished, it should contain only one .end directive where it belongs at the very end of your program. All right, they're very directive here. I think we're at the part where we're actually going to be typing something in soon. And not to my Helix editor, but to like the real Atari. Well, to the fake emulated Atari. Do any of you actually use your real Atari? Like, that's just so cool. But it'd be harder for me to actually like show it. I'd have to like figure out, I don't know. First I have to get an Atari. I don't even know how to get one. But there's just logistics. Let's continue. Assembling an assembly language program. Okay, are you ready to write and run your first assembly language program? Yes, really. Like, I was so ready from chapter 1, and now I'm 68 pages in. No, 66 pages in, and I still haven't typed one. Please let me type one. Good. Then sit down at your computer, turn on your disk drive and your video monitor, and boot up your assembler if it's on a disk. Or slip your assembler cartridge, if that's the kind of assembler you've got, into the cartridge slot in your Atari. All right, guys. So I kind of like played around with Altera to figure out how to use a disk drive because I had no idea like how Atari disk drives work. So I think we'll be able to handle that. Let us switch Altera to the Max 65 assembler, I guess. I don't think you guys can see this when I click here, right? So I probably should show my whole screen so that you guys can see how I'm doing this. Let me do that. All right, so we got the whole screen on here now. And in Altera, we're going to attach cartridge, I think. Yeah, I'm not an expert here. Atari. ROMs, maybe? Max 65. And looks like I have 2. Oh, what am I doing? What is this? Select cartridge mapper. Alright, I have no idea what this means. Show. Alright, well, usually the default one works, so maybe this is good. Looks like we are on Max 65 version 1.02. So that's cool. Let me explain what I did for the DOS stuff too. There is this site that's very nice. Um, well, this page, I guess, that I found for how to use the disk drive. And I read it and I kind of figured out that, like, apparently to use your disk drive, you need a DOS. You need a to load DOS in your disk drive. Like, you put a disk that is DOS in your disk drive, I think, first, which is kind of funny. Maybe, like, please tell me here or in the comments that, like, do you usually make notes as you read, or is it a matter of committing to memory? I have, um, I have a cheat sheet that I usually use as, like, in GitHub, like a gist, and I haven't made one for Atari yet because I don't know how much I'll need to memorize. That was a question someone asked in chat. And I'm very, very tempted to, like, to start doing that. But most likely what I try to do is remember that I know something vaguely and that I'll know to go back to the Atari roots. Um, so that's kind of like how I do it. But I definitely have other, like, things, like when I was doing COBOL recently, I had to make a cheat sheet that just helps me remember stuff because there's so many, like, weird terms for mainframes. It's insane. So far I haven't done stuff. No, but I'm sure I will. All right, so what I was saying was we need Atari DOS, and I found Atari DOS by, like, typing in Atari DOS like 2.5 or something like that, and found this page. I'll put this all in the description also, and then you can just download it. And after you download it, you unpack it, and then I told this thing, I did like disk drives, I think, and then we can I downloaded it. It had a DOS 2.5 folder, and ATR is what the disk files look like, and I just load that, and now it's set for disk 1, and I do read only because I don't want to screw up my DOS disk. And then you press F5 and it should just load. Oh, maybe it's Shift F5 here. I guess because it has my cartridge. 1 second. I don't know. I'm a little scared that, like, let me take the cartridge off. Okay, so now when I reset, I think I have DOS now because it's in the drive. Yeah, so now I have DOS. And then I will attach my cartridge again. Max 6502 ROM. And here we go. So maybe you have to do something like that. I'm kind of like feeling my way in the dark here. So if I'm wrong, please let me know in comments or in chat. Okay, so now I'm going back to the Atari view here. Except I've lost my... There we go. We're here, right? So we will get rid of Wes term and we'll show Atari. Okay, now this looks right. Assembling an assembly language program. Here we go. Your assembler will be ready to go when the word edit, the assembly language equivalent to BASIC's ready prompt, appears on your video monitor. Do we have edit? We do have edit. So we are good so far. Okay, sorry. If that doesn't happen, then check stuff. Well, we got it. When you have your assembler up and running, you can put a blank formatted disk into your disk drive. This disk should have a set of DOS files recorded on it so that your disk data will boot automatically when you turn the computer on. without any need for a special master disk. Oh, so you can put DOS into your disk. If you put every program in this book on your data disk, you'll still have room for data for a set of DOS files, and they'll save you quite a bit of time. All right, now I have no idea how to do this, so let me see. I did create a blank disk, I think. Disk drive, and then here, what is this, eject? This doesn't, no, this doesn't create a disk. I think it was somewhere here where we can like create a disk, attach. Disk drive, open image, maybe not here. System, input. Oh, you're not seeing this. Let me go back to, so what I did is I went into disk drive and I just clicked on this eject button. But now I'm trying to figure out how do we actually create like a disk. Disk Explorer. That's not it. Advanced configuration. Oh dear, I thought I knew how to do this. This is where you see I get lost. Does anyone here have an Atari that they know how to do this? Input mapping, setup, calibrate, system profiles. Maybe it's under configuration. View, file, boot image, recently booted, open image, disk drive, attach disk. That's not it, right? No. I think it was in that website that I was looking at earlier. One of these. Here it is. How do we... Oh, right. It's like it was a button on disk drives, and then it was one of these buttons. So instead of... Here it is. It's this like this caret button. So then we do new disk. New disk. Single density, file system DOS. Does that mean this thing is going to have DOS in it? New disk. We'll call this like roots. Oh, we can't give it a name. Not been saved. Sure, cancel. New disk. Save disk, I guess. And we'll call this roots ATR. Read write. But I don't know if this thing has DOS in it now, and I don't know how to put DOS in it. So that's kind of activating DOS 2.5. Next, in order to select menu, again, warm reset, formatting blank disk. I wonder if that's format with DOS 2.5. That's what it just did. I think it said with DOS, right? Maybe that means that it can... So why don't I get rid of the cartridge for a second? Detach cartridge on this disk. Oh no. That's really not good, right? We don't have DOS in this disk then. Disk drives. We have this, but it doesn't have DOS in it. All right, so that's not good. Let's go and boot the other drive up, which is our disk DOS drive. All right, so now we're able to boot, but what I don't know is how to add DOS to this disk. Maybe we just have to format. Let's see. format disk. Maybe I'll just switch the disk. Create memsave. Format single. Write DOS files. There we go. Look at that. So why don't I, let me see. Do I type H first? Drive to write DOS files too. So let's change the disk. Or maybe I'll just put it in D2, right? Maybe that'll work. Here we go. How do I type? D2 maybe? Type Y to write DOS files to drive to. We did it, right? Okay. So now if I go back and I basically get rid of this, we just eject this and we load. Can I, oh, is this thing saved? Can I, disk image has not been saved. How do I save it then? Boot image, open image, disk drives, cassette, load state, save state, save firmware, view, system, profile, warm set. Have no idea how I'm supposed to like save this file. Oh, save disk maybe. Maybe it's just save disk. Okay, cool. So it's just like, maybe it's like in RAM cache until you actually click save disk, and now I can eject, and now I can like load this as my first disk, and now if I reboot with Shift F5, hey, look, it worked. Now we have DOS on our new disk. That was a little bit difficult, huh? Takes a little bit out of the soul. All right, now we put the cartridge back on. And we're good to go. By the way, if you're trying to do this now in this video because of the stream, then like you can go to the previous video and get the links for Mac 65 and all that. It should be there if you want to download that. All right. Now I think we can go back here and we can now, I think we can do this. So we've done this. If you put every program in, so now we're good. I hope, I really hope, because otherwise I'm going to type this program and it won't work. I won't be able to save it. When the edit prompt comes up on your screen, you can type the addition program at the beginning of this chapter into your computer. As you type the program, be very careful about the spacing you use. I'm going to be very, very careful. Mac 65 and the Atari assembler cartridge are a bit fussy about yeah, you told us this. In the lines that contain semicolons, remember that there should be only one space between the line number and the semicolon. In line 40, however, what was line 40? There should be at least two spaces between the line number and the asterisk, since asterisk is a directive, right? So that was over here, and we see that yeah, the directive on line 40 in my screen has an extra space. Makes sense. All right. In line 60, there should be one space. Yeah, they're telling us all these things. Let us just start typing. It's here, so why don't we just copy this? 10 semicolon 20 semicolon. Right? Now I'm getting nervous. 30 semicolon 40. We need two spaces because this is the label and now this is a directive. So star equals $0600. Now we do line 50, which is a comment. Line 60 is a label. So it goes here. ADD NRS. Clear. No, this is clear the decimal mode, whatever it is. What was that thing called? Yeah, I should start writing down what these things are. It's just weird, like it's just like this thing. We're using plain binary numbers, not binary coded decimal. So this line will clear the decimal mode flag. Clear decimal mode. So that's CLD, clear decimal mode. All right, perfect. Where are we? Line 60, we just cleared decimal mode. 72 spaces because it's not a label. Right? Yeah. CLC. This is clear carry. 80, 2 spaces. Load accumulator with the literal number 2. 90. ADC. This is add whatever's in the accumulator with carry. And then we have 100. This gets a little funky because now we need 2 spaces and they no longer line up. Store this into hexadecimal address CB and then return from subroutine and then directive.end. Alright, so that was edit. After you've typed your source listing of program 1 into your computer, type the word list and you should see a screen display that looks like this. Okay, let's type list. Yep. Oh wow, it moved it and it aligned it. That's pretty neat, right? Does anyone see any errors? I used to like, you ever have like tests in like, school, like high school or whatever, and they give you like time to do the exam? I guess university too, like I would be always like one of the first people finished, but that doesn't mean like I did well. It just meant like I just finished and they're like, "Oh, did you check your answers?" I'm like, "I literally don't know how to do that." Like it's really hard to do this, to compare things or anyway, I'm off on a tangent. If you have a line printer, you can now print your program out on paper. Just type list $P:. I bet like there's a way to attach a printer in here, but I'm not that interested in it because I could just like snap the screen. But maybe one day we'll figure out how to attach a printer and then maybe we can even like print directly from our Atari into like some AirPrint, printer or something like that. Anyway, it's a moot point. I literally don't have a printer. It doesn't matter. Easy enough, right? No sooner typed than done. Now, if your listing looks all right, you can save your program on a disk. Let's see if this works. Just make sure that a formatted disk, preferably a blank one, is in your disk drive and the ready light is on. Then type list D. We're in D, right? Our drive. Yeah, I think our drive is on D. Add numbers dot source. Whoa, did you see that? There was like a little number 1 here. I guess like that was our drive sort of doing stuff. But we didn't get an error, so that's really good. The top red light on your disk drive should now go on, and the disk you're storing your program on should start to spin. When your disk drive's busy light goes off, your source code should be safely recorded on disk under the file name $d colon add nrs.source. We suggest you keep your add nrs.source source code in a safe place since we'll be working some more with this program in later chapters. Right now, in fact, you can use that very source code to assemble your program. To do just that, just keep your source code disk in your disk, type in your disk, keep your assembler editor cartridge in your computer, and type the command ASM. This is a big deal, guys. Let's go. Holy crap. Error 0. That looks right, right? And notice the page 6 here of memory that they talked about earlier. So that's all good. All right. As soon as you've done that, the computer should present you with a screen display that looks something like this. Yeah, we kind of saw some of this fly by. And bytes F1. Oh, bytes free. It just kind of went over the screen. Page 2, symbols 0600 add NRS. Yep. So that's like the beginning of the program in memory, and that's the name of the subroutine. Edit. If you've made any typing errors in your program, this is where you'll probably find out about them. If your assembler finds an error in a line, it will sound a beep and display an error message. It may not be able to spot every error you make, but when it does catch one, it will print an error number on your screen just like a basic interpreter does. And you can find out what the number means by consulting your Mac65 manual. Oh, so we'll probably need that. If your assembler finds any errors in your program, you can now type list and go back and correct them. All right, so let us make an error. We'll do like in 70, instead of doing 2 spaces CLC, we'll do CLC in the label field. You can see it's in the wrong place. And now I type ASM. Error 0. Oh, it just thinks that's the name of the label now. Oh, this is so tricky, you know, like that's really tricky because it doesn't say like, hey, that was a reserved opcode name in the label field. It doesn't even make that check. That's crazy. And if I don't pass in an operand, error, it tells me right away. All right. All right, that's good. I think we have an idea now. You'll know that your program has been assembled correctly and that you have just written an assembly and assembled your first assembly language program. This depends on the version of DOS you have. Yep. A difference between assemblers. Okay. I think for me, let's take a look at this. Now we've come to an important difference between the Atari assembler editor cartridge and the Mac65 assembler. When you assemble a source code program using the Atari assembler editor cartridge, the object code generated by the assembly process is automatically entered into your computer's memory. When you assemble a program using the Mac65 assembler, however, the object code is not automatically stored in memory unless you use a special directive. That directive is .opt. The option directive is used in this format: 05.opt obj. So I guess that means like you put it in line number 05 between, you know, I guess in the very beginning, like very first thing. If you have a Mac65 assembler, you can insert that line into your ADD-NRS program, and the program will automatically be stored as RAM as it is assembled. So why don't we write that? Why is there a dot? I think that's wrong. I think it's meant to be space space dot object, right? Because the op is this is the directive, but it needs to have two spaces to be in the directive column. Um, let's see. What's next? Once you've stored your program in RAM, you can do just about anything with your program you like. You'd like, no? Run it, print it on paper, store it on a disk, or store it in your computer's memory. Before you do any of those things, however, it might be a good idea to take a closer look at the add NRS program. Look, now they put a dot here. Yeah, this is just like 1980s editing. The object code listing of your program in its final assembled form. In column 1 of your object code listing, you'll see the memory addresses in which your addition will be stored after it has been loaded into your computer's memory. In column 2 is the actual object code listing of your program. It's this column that we will show you in hexadecimal notation, the actual machine code version of the program. It's what the numbers in column, this is what the numbers in column 2 mean. Ah, I see. This is like here, you see where it says D8. So this is the memory location. I think column 1 of you'll see the memory addresses where your addition will be stored. So when I read this, I was like, your addition, so you mean the number 4? But no, they meant like where your program will be stored. So you see 600 is D8. And now we can see that D8 means clear status registers decimal mode flag. And then clear carry is 18. Yeah, that makes sense. A902, load accumulated with the number 2. But notice R says A9. That's kind of funny, right? It does say A9, right? And this is load 2. So if I look at the program here, load number 2, that's correct, right? Yeah, that's correct. So somehow this doesn't line up, but maybe it doesn't matter, right? Let's look at that again. And where are we now? 6902 is the add with carry. Store CB is 85CB, looks correct. And RTS 60 return to subroutine, return from subroutine. So that's that. You can print. Wow, I guess back in the day, everyone was into printing, right? I mean, because the screen was harder to see if you wanted to work on something, maybe by printing it, you could like have it all, and then you can like edit it. You've now written, assembled, printed your first assembly language program, and that means we're almost ready to end this programming session. But before you turn off your computer, it wouldn't be a bad idea to save the object code of our program on disk. So let's do that now. List or save? I do want to do another save though, because didn't we've changed the code. So I wonder, can I just like use the same save command? Oh, the same list command? Let's try. List d add nrs.source. I guess so. So it probably overwrote it. By the way, that's what I mean by I don't take notes. Like, I forget, but I know I did it so I can look for it. All right. But to save the object code of an assembly language code, there are two other commands. One is save and the other is bsave. If you're using a Mac 65 assembler, the command to use at this point to save the object code is bsave. If you're using Atari, it's just save. Save and bsave commands are used in exactly the same way, however. Here's how it's done. First, type the command ASM and your computer will assemble the source code of your addition program. If you've already done that, there's no harm doing it again. Let's do it again. Let's do it again. All right. That was fun. Next, look at column 1 of the object code listing on your screen and note the memory address that your program has been assembled into. Does that mean this? Does it mean this? Don't know. But it's going to be 0600 anyway, right? Yeah. The program should start at memory address $0600. Dollar sign means hexadecimal, and should end at memory address 0609. Yep. So this is the line to type if you have a Mac 65 assembler. All right, let's type this line. bsave d addnrs dot obj less than 0600, comma 0609. All right, you saw the little 1 come up again, so I'm guessing it did that. Busy lie goes off. The object code listing of our addition program should be safely stored in the disk under file name addnrs.obj. Perfect. Did it work? Now, let's see whether all of that listing and saving worked. First, type new and press the return key. All right, so we type new, return. Oh, wait. Yeah, there's nothing now. Clear your computer's memory, then type enter. Your disk drive should spin and the word edit should appear. So enter #d addnrs dot source. Let's do that. Enter d addnrs dot source. Okay. Now if you type the word list, you should see your program. Hey, yeah, and it has the updated one with the opt obj. So that's cool. Should come up. Now if you assembler type bload. All right, so we'll do bload. Bload. Since we're using Mac 65 assembly, we type bload addnrs.obj and hit return. That worked. We don't need this. Your disk drive should now load the object code of addnrs into your computer, and the word edit should appear once more. Then if you type the command ASM again, the assembly code listing of addnrs program should appear on your video screen. Yeah, perfect. You've accomplished quite a bit in this chapter. You've written and assembled your first assembly language program, and hopefully you have a pretty good understanding of how it was all done. You've saved both your source code listing and your assembly code listing on disk. If you have a printer, you've also printed out both listings on paper. And now in Chapter 5, you're going to learn how to run an assembly language program. So I think I'll stop here. How long has this been? Does this thing tell us like how long we've been on? 1 hour and 13 minutes. So that's good. Does anyone have any questions or anything like that? Since this is also going to be a video, if you like it, then do like and subscribe. There's the Discord server. I told you about that. It's all in the description. So I'm going to stop the video now. We'll stay on the stream for a little while longer. Thank you for watching.